Climate change. We've all heard the warning, 12 years to change what we're doing. But there's a side of it that often falls to the wayside, ocean acidification.
As humans pump carbon dioxide into the atmosphere, it is absorbed by the oceans, where it forms carbonic acid. Carbonic acid lowers the pH of the oceans, which both depletes carbonate that marine species use to build their shells and dissolves the shells themselves.
What's the problem with this? Well, species are adapted to live in a certain environment with a certain pH. Therefore, a change in pH can decrease population.
By releasing carbon dioxide into the atmosphere, we damage marine habitats that species rely on.
So why exactly does extra carbon dioxide create so many problems? The answer lies in the three chemical equations that represent the reaction of carbon dioxide with seawater. In reality, all three of these reactions take place simultaneously, but let's discuss them as if they were sequential.
When atmospheric CO2 first dissolves in the ocean, it forms carbonic acid. The first reaction proceeds to equilibrium. Next, the carbonic acid decomposes into a hydrogen ion and a bicarbonate ion. This reaction proceeds to equilibrium as well. Finally, some of the bicarbonate decomposes one more time into a hydrogen ion and a regular carbonate ion.
Since all three reactions have Ka values lower than 1, fewer reactants and products are present at equilibrium. However, since this third reaction's Ka value, 4.69 times 10 to the negative 11th, is the lowest of all, it produces the least product and isn't considered a primary reaction. This is because removing the second hydrogen from the carbonic acid requires a higher ionization energy. These species can be considered to be in a single equilibrium, with hydrogen ions and bicarbonate being products of the dissolved carbon dioxide. Usually the system creates ocean water that's slightly basic, with a pH of 8.1. But what if something changed?
When more atmospheric CO2 is added, by Le Chatelier's principle, the system produces more carbonic acid in an attempt to re-establish equilibrium. What then? Since more carbonic acid is now present in the system, the second reaction also shifts right to produce more hydrogen and bicarbonate ions. The hydrogen ion concentration increases and the pH lowers. Due to the increased concentration of hydrogen and bicarbonate ions, carbonate becomes a buffer. In excess of H+ ions, the third reaction shifts left. It becomes bicarbonate as the system tries to re-establish equilibrium, and due to its lower Ka value, shifts further left than the other two reactions. As a result, as the pH lowers as more CO2 is dissolved in water, carbonate present in the seawater actually decreases due to the varying rates and directions of all three reactions happening at the same time.
This creates a problem. As the concentration of carbonate lowers, animals requiring it to build calcium carbonate shells or exoskeletons have fewer resources to work with. A second issue also comes up. Since hydrogen is more electronegative than calcium, it's more reactive with carbonate than calcium is. If the pH of seawater is too low, the excess H+ ions will actually dissolve the shells of calcifying animals to bond with the carbonate ions.
If current trends continue, the oceans could acidify to a pH of 7.8 by 2100. It may not sound like much, but it's enough to create a twofold issue that can wreak havoc on the ocean's vibrant ecosystems. Ocean acidification has drastic effects on calcifying species such as corals, shellfish, and plankton. Organisms' calcium carbonate shells are affected because there's less bicarbonate for these species to use, which means that these shells will begin to dissolve.
Ocean acidification also limits the ability of reef-building corals to build their skeletons and causes them to erode faster than they can build. Elkhorn coral are an example of this species that may not be able to successfully fertilize, have larval settlements, and in the end survive.
When hard corals break down, a loss of habitat and biodiversity will occur. Shellfish are also negatively affected, and about 1 billion people rely on shellfish for a primary source of protein.
Plankton form the base of the food chain, and ocean acidification puts plankton at risk, which is very dangerous to the food chain as a whole.
There are a few ways we can reduce these negative effects. Minimizing fossil fuel use is the first and most important step in minimizing the effects of climate change. This means supporting businesses that use renewable energy sources, as well as voting for candidates that support the environment. You can also spread awareness of the dangers of ocean acidification and how it affects us as humans.
We've established that humans are a force that drives climate change.
Now we're left with a decision.
Can we change ourselves to use this force for good?